Thank you, Sam and Claude. Today I'd like to talk about microbial induced concrete corrosion. I'd like to provide a little bit of a background on the topic and then get into a discussion of some of the standardized testing that's underway. Now, we all know that this is the season for March Madness, and it's a very exciting time, and it kind of takes us back to the days of Gene Hackman, his Hickory team, and our good friend Ollie, who in a class project reminded us that progress is electricity, school consolidation, second farm tractors, but most importantly, it has to do with indoor plumbing. And it's really that indoor plumbing that is what we're here to talk about today. And it's really how that indoor plumbing functions and connects with the wastewater treatment infrastructure that's really the important piece of this. Now, as you know, ASCE provides a report card, and one of the areas that they evaluate in the report card is the wastewater treatment facilities and infrastructure throughout the United States. Now, unfortunately, this has been getting a grade of D over the last several years. And the thing that we really need to think about this is about 20% of the wastewater treatment facilities and homes are connected to septic systems. The other 80% are connected to about 16,000 treatment plants, 15 to 20% of which have exceeded their design life. Each year, there's going to be about $18 per customer that's spent to replace the pipes. So as we think about this and we start to look at where concrete's place is in this infrastructure, what we can really see is that concrete has really been the material of choice for sewer pipes, for manholes, for lift stations, for wastewater treatment facilities, and for septic tanks. And part of the reason for this is, one, the concrete is really resistant to buoyant forces. Two, in general, the concrete is quite durable and long-lasting. And three, it's a really robust infrastructure material. However, as I say that our concrete has been durable, we start to see that some of our concrete infrastructure in the sewer infrastructure can start to decay and degrade like we see in these pictures. And this is really the decay that's consistent with microbial corrosion. And if we look at how much decay happens annually in a well-functioning system, this could be fractions of a millimeter every year. However, in systems that are undergoing massive degradation, you can see tens of millimeters of degradation happening annually. So what we really want to do today is we really want to help to shine a little bit of light on what's happening in this underground infrastructure and what are some of the new tests that are coming out to really help guide us in the ways that these systems should be designed moving forward. Now, I want to point out that currently ACI has been really silent on this really important topic. However, I do want to tip my hat to ACI 201 because they've really set up a task force, and that task force is hosting this session that's really starting to create this discussion and really starting to assemble the information, document the information, and really put it out there to provide guidance and leadership on this for the industry. So what is microbial induced concrete corrosion? Well, the bacteria that are inside of the sewage system are going to really work to reduce some of the sulfate that's in the system. And in doing this, they're going to produce hydrogen sulfide. And while that hydrogen sulfide is produced in the liquid form, it's going to be, due to Henry's law, it's going to leave the liquid system and it's going to get into the headspace. And when it's in the headspace, it can actually fuel some of the bacteria. So the bacteria are going to actually be using this. That's going to fuel them. They're going to in turn produce sulfuric acid, which can result in damage to the concrete. And I want to point out that this is not only something that damages concrete structures, but you can see the same type of damage that's happening in steel structures as well. Here you can see some rusticles forming on one of our ships that has crashed and is at the bottom of the sea. But when we talk about this for concrete, even though the industry refers to it as microbial-induced concrete corrosion, it's really not metallic corrosion. It's really the degradation of the concrete itself. It's the acid degradation of the concrete itself that's causing that decay. So if we look into this overview again, as we mentioned before, the sulfates are going to be created. There's going to be sulfides created in the solution. Henry's law is going to allow H2S to go into the headspace. When that is in the headspace, we're going to see that this H2S works with the bacteria both at the crown of the system and really at the water line. In the bacteria consuming this, they're going to produce acid. That acid is going to be responsible for the degradation of our concrete. And that degradation starts to look like what we see in this picture here. So what we can see is on our right-hand side, we see a degradation layer that's starting to form where that concrete really starts to decay mainly at the surface and starts to work its way in, frequently sort of peeling itself back like an onion. Here we can see a lift station. In this manhole cover, in this lift station, you can see that the concrete is really just flaking off as we look at that surface. So what we're really trying to do is figure out how do we get a better handle on this and what is the process of degradation really look like? And it's really at this point where we want to talk about the three stages, sorry, not the three stooges, the three stages of microbial degradation. So if we start to get into this, our three stages are not going to be molary and curly. Our three stages are really going to be outlined like we see on this diagram that we see on the right-hand side of the image here. When our concrete is originally produced, it has a pH of around 12.5 to 14. So this high pH is really going to help the concrete to be resistant to the attachment of bacteria. However, almost initially when that concrete goes into service, you'll see the pH, especially in a sewer environment, you'll see that pH drop from about 12.5 down to a value of about 10 to 11. This first stage is commonly referred to as the carbonation stage. Those we're going to talk about in a few sentences. This may be a little bit of a misnomer, and we're really focused in on all the items that occur that correspond to the pH starting to be lowered. The second stage really starts to refer to where the biofilm starts to attach on the system. So it's really at this point where we start to see the bacteria and the biofilm really attaching at the surface. And once it starts to attach, once it starts to become established, we'll see the pH drop from about 10, very low values, anywhere from about 4 or 5, all the way down to things like around a 0.5. It's really in this final stage where we start to see massive losses of the concrete thickness as a function of time. So let's dive into this a little. This may be a little bit of a misnomer, and we're really focused on all the items that occur that correspond to the pH starting to be lowered. The second stage really starts to refer to where the biofilm starts to attach on the system. So it's really at this point where we start to see the bacteria and the biofilm really attaching at the surface. And once it starts to attach, once it starts to become established, we'll see the pH drop from about 10 down to a pH of about 4 to 6. Right? The degradation itself is particularly slow in this region, but this region is really where the bacteria starts to attach and starts that overall progression toward more substantial deterioration. The third stage, the final stage of what we're looking at here is stage 3. And this is the stage where we really start to see the pH drop excessively. This is really where we really start to see a large amount of acid being produced, and we really start to see chemical acidification really taking over and dropping the pH from this value of 4 to 6 down to very, very low values, anywhere from about 4 or 5, all the way down to things like around a 0.5. It's really in this final stage where we start to see massive losses of the concrete thickness as a function of time. So let's dive into this a little bit more, and let's talk about each one of these stages. As we mentioned, it's very, very difficult for the concrete to stay at a high pH. Now, part of this has been described by carbonation, which is the movement of CO2 gas through the pore solution and the reaction with the calcium hydroxide that helps to carbonate the system by tying up that calcium hydroxide. It's no longer able to act as a buffer. It can't maintain the pH at a high level, so the pH starts to drop. However, in concrete piping, especially in the wastewater and water treatment facilities, what you'll really notice is there's a second effect that helps this pH to drop. And this is really the dissolution of the calcium hydroxide simply due to the presence of a fluid being there. So the fluid itself helps to dissolve the calcium hydroxide, which leaches out of the system. And as it leaches out of the system, that causes the pH to drop. So even though we talk about this as carbonation, it's actually a combination of both of those effects. The final thing I wanted to really mention here is this isn't classic carbonation where we worry about how many inches into our concrete the CO2 front is really propagating. Here, we're worried about really where the bacteria are going to come in contact. So we're dealing with a very much localized surface phenomena. This can be taking place only within, let's say, the outer millimeter of the sample, because it's that outer millimeter where the biofilm is really going to start to attach. So this is very, very difficult to prevent. And in fact, most people have focused on not really worrying about phase 1, but focusing more on phases 2 and 3 as ways to help prevent and mitigate the deterioration that's taking place in the overall system. So if we jump into this a little bit more, we can now start to talk about stage 2. And in stage 2, you can think about this as the attachment phase. This is really where the biofilm starts to become established on the surface of the concrete. It starts to become more established, and a big part of this is the bacteria are going to start to grow, and they're going to start to go into succession when they're happy. And this happiness and this growth phase is really going to be dependent on several things. It's going to be dependent upon the temperature of the system. The higher the temperature, within reason, the faster the bacterial growth is going to be taking place. If there's moisture and there's availability to nutrients, we're going to see more and more bacterial growth and development taking place in that system. And also the surface texture can play a major role in how happy the bacteria is in this phase. With more surface texture, more nooks and crannies, what you can start to see is that bacteria finds it a little bit easier to attach to the surface, right? You could think about might be ways here where we could make it more difficult for the bacteria to start to attach. So one of those things that you could think about is you could actually change the surface texture. You could make it more difficult for the bacteria or the biofilm to attach to the surface. Another thing that's discussed about a way to sort of interrupt stage 2 or phase 2 types of processes would be things like antimicrobial additives. These antimicrobial additives may prevent the biofilm from becoming established and may result in this not resulting in a pH drop and maintaining the pH at a much higher level without the establishment of the biofilm. And what that might actually do is it might actually short circuit the degradation process right here. And it's really important that we understand these 3 stages so that we can understand where the different materials that might be used could really be effective. If we get into the third stage, this third stage is really where that biofilm itself is established, and I've drawn the biofilm as these little green guys from something like Pac-Man. But the basic idea here is that biofilm that's been established here is going to start producing the sulfuric acid that we're going to start to see on the surface, and that acid is going to start to degrade the surface. And the lower the pH, right? So as we sort of go clockwise in this circle, we're seeing systems with lower and lower pHs as we go in the clockwise direction. And the lower the pH, the more acidic the environment, the faster that rate of degradation is going to occur. The more millimeters per year are going to be happening in those systems. And this is really driven by the fact that it's a much more acidic environment. And we're going to see sort of a self-fulfilling cycle here where more acid is being produced. Therefore, the surface is deteriorating. The pH is dropping lower and lower. More and more acid is being produced. And you'll see this as it works. This is really driven by the fact that it's a much more acidic environment. And we're going to see sort of a self-fulfilling cycle here where more acid is being produced. Therefore, the surface is deteriorating. The pH is dropping lower and lower. More and more acid is being produced. And you'll see this as it works its way through the system. So we really want to stop now and we want to pause and we want to say, well, what is it that we actually know at this point? What is it that we know? What is it that we understand? Well, the first thing we understand is that there is a problem of sewer damage. The second thing that we know is it's a 3-stage phenomena: pH reduction, attachment, and then really chemical acidification and deterioration. And now the question comes up is there a standardized test for this? And unfortunately, measuring things like compressive strength are not really the standard test that we necessarily want to be using in the system. Now, I want to again tip the hat a little bit to ASTMC 13 because they've been really stepping up to try to get their arms around this and really put some standardization forward. The committee's been incredibly active to develop some of the first standards worldwide on this particular topic. And the three that I'm going to mention today are ASTMC 1894, which is really a guide. It provides an overview of the problem. It provides several of the things that we just talked about, and then talks about what tests work in which of the different stages. The second thing I'm going to mention is ASTMC 1904, which is really the biogenic acidification part. And you can think of this primarily as stage 2, although there is a component of this that gets into stage 3. And the third part of this is ASTM 1898. And this is really an update of ASTMC 267. And it's a chemical acidification test. And what this procedure has really done is it's helped to reduce some of the loopholes or tighten up a little bit of what was commonly being done in ASTMC 267. So let's jump into this a little bit more and talk a little bit about what each one of these items is doing. So the first document I mentioned really provides guidance on microbial-induced concrete corrosion of concrete products. It discusses the test methods and really starts to talk about which test methods should be used when and where and why. It talks about things like the H2S chambers that you see on our right-hand side here. It talks about some of the reasons why you might want to use those, but it also talks about what are some of the challenges with those, most notably the fact that you have to use H2S gas, which is really difficult to work with, and it's also dangerous to work with. It then says in stage 2, you could have an alternative type of test, and it's going to be that biogenic test that we're going to be talking about in a few seconds here. And it's going to talk about some of those differences. It's also going to talk about when and where you should use a chemical acidification test. And it's really going to focus on the fact that this is only appropriate for stage 3 if you've already established the bacteria colonies on the system, you've already had attachment, and you're already into acid degradation. This isn't going to be the type of test that can be used to evaluate things like antimicrobial additives because it doesn't evaluate the attachment phase. So if we look at the test method that's out there to really look at the biogenic acidification, this is really ASTMC 1904. And I want to just mention that this really is divided into 3 main pieces. The first piece really looks at solutions. So the idea here is you could actually look at an antimicrobial solution. You could look at a conventional system, and you could essentially see how rapidly the pH changes in those systems. So in a control sample, you'll see the red line here where the pH starts to drop over time because of the bacteria producing acid in the overall system, where the antimicrobial itself can help to prevent that from happening and maintain a high pH. So the idea behind this is a simple way to start to qualify different antimicrobial additives. This also has a component where it gets into option B1 and option B2, where you can now start to test paste and mortar combinations, either using a defined proportion or proportions that you would define on yourself to evaluate different materials and how they relate to the degradation process. The final portion of this really starts to get into doing the same type of work for paste and mortars, but now allowing it to go from stage 2 all the way into stage 3. So to really drive from biogenic acidification, which is really stage 2, into stage 3 and get into chemical and acid attack. Berkan Isgor is going to talk about this much more in his talk that's upcoming in just a few minutes, right? It will use things like thin paste to do these types of measurements, but again, I'll let him get into that in greater detail. The final test is really getting into what this test is going to be able to do finally is really getting into being able to simulate biogenic acidification, understanding the attachment phase, and really taking that all the way through, as I mentioned, in the final state to stages 2 and 3. The final test that we're going to talk about is ASTMC 1898, and this is really a revision of ASTMC 267. And what we really wanted to do was we wanted to directly capture some of the loopholes or the areas where there were gray areas in ASTM C267 to be able to evaluate this a little bit more in a more controlled fashion. So the idea behind this is chemical acidification is taking place in the system. We've fixed the sample to solution ratio. We've fixed the exposure times. We've fixed how often the acids have to be replaced. And we talk about some of the things that we're going to measure in these cases. So it really emphasizes a lot of the items that House found, really helps to identify several of the things in ASTM C267 that can be clarified, and really helps to make this a much stronger test. I really want to focus, though, and I really want to say that this is really all about stage 3, where we're dealing with chemical acidification. So in conclusion, I want to try to bring this home and basically mention substantial work is underway to better understand and predict biogenic acidification. There is clear evidence to show that there's a 3-stage process: carbonation, attachment, and degradation. And the attachment phase is evaluated using a biogenic test. The degradation phase can be evaluated using either biogenic or chemical acidification. 3 standards have been developed, primarily led by ASTM C13 with the National Precast Concrete Association and the American Concrete Pipe Association, and help from Oregon State. Substantial changes in how we view this degradation are really starting to occur in the industry nationwide and again throughout the world. And this is really helping us to get a better handle on how we talk about innovative cementitious systems, how we talk about innovative topical treatments, and how we really start to approach moving this from an empirical type of science into something that we can start to predict and something that we can model. Again, I want to thank you very much for taking the time to listen, and I want to thank our moderators for organizing a great session, and I look forward to talking with you.